Okay, so it's our pleasure to welcome back Ovidiu Savin, who's from Columbia University, and he's giving a talk on Monge-Ampère equation. That's a follow-up from last week's talk. We appreciate his coming to us and giving us a series of talks. And go ahead and thank you very much.
Okay, thank you for the introduction. So this is the second lecture. I'll just review briefly what we discussed last time. So the Monge-Ampère equation, we try to solve the equation determinant of the square of u being prescribing f of x. And we look on the space of convex functions u from some domain omega in Rn with values in R. And the last time we discussed some general, some generalities about the Monge-Ampère equation, how it relates to Laplace equation. But what was very important, what the key properties for the Monge-Ampère equation are the affine invariance. So if you have U and you take a matrix A with determinant of A equal to 1, you call such AX is then an affine deformation, and you look at the rescale function U tilde of X being U of AX, which simply means that in the X space here, you're just doing an affine deformation and you keep the height the same, right? Then you solve essentially the same equation. You solve determinant of the square of u is f tilde, where f tilde change exactly the same as u. Sort of if the value of f on top at the point x became f of ax. So the right-hand side transforms exactly the same as the solution. Yeah. In particular, if the right-hand side is 1, it's going to remain 1. So this is the key property that our equation has an affine invariance, something that, and this affine group is much bigger than the rigid motions group. Yeah, has many more dimensions. And the second property of the Monge-Ampère operator is that, let's say, if you raise the determinant of a matrix to the power 1 over m. So here I'm thinking that m is a matrix standing for the Hessian, right? Then this becomes a homogeneous of degree 1 operator on the space of matrices. That's why I raise it to the power 1 over m, 1 over n, but it can be viewed as an infimum of linear maps. And these linear maps are nothing but the sum of aij, if you want mij, m small ij are the entries of capital M, among all positive definite matrices A with the determinant of A being equal to 1. So here again, one more time, you see the affine invariance of the right-hand side. When the right-hand side is affine invariant, but it tells you the determinant raised to the power 1 over n is an infimum of these linear functions in M, right? So for each capital A, I have a linear function M, but I'm taking the infimum as the matrix A is moving. So for this reason, the determinant of M to the power 1 over n is a concave operator in the space of matrices. So here, capital M, the space of matrices, I think the symmetric n times m matrices that are positive definite. Yeah. Positive definite because you only look for convex function, and because only on the space of positive matrices, the determinant is increasing, and now our operator is elliptic. Yeah. Okay, so these are the general things that we discussed last time. Now, I want to discuss about, so we stopped at the point, at the place when we talked about the Dirichlet problem. So the Dirichlet problem, we really want to solve the Monge-Ampère equation. We are given data, f being a right-hand side, phi being a boundary data. Here in this picture, the graph of phi is denoted with the purple color. And we try to find a function u that agrees with phi on the boundary of omega, but solves the determinant of this square of equal to f inside. And Caffarelli, Nirenberg, and Sprack, and independently Krylov, they show that there is always a unique classical solution, UC2. In fact, it is better if the data is better, if f is smooth and phi is smooth, then you would be C infinity. So there is always a classical solution, provided that the right-hand side is at least C2 and has to be strictly positive everywhere, including the boundary. Yeah, so the right-hand side, we are not allowing for the right-hand side to tend to 0 as you approach the boundary. It has to be everywhere positive, like 1. Let's think that the right-hand side is 1. It's constantly 1. And provided that the boundary, that the domain is sufficiently regular and uniformly convex, has to be uniformly convex. And the boundary data is sufficiently regular. So let's say if you give me enough smoothness on the boundary data and the right-hand side and the domain, and uniform convexity of the domain, then you can solve this problem. What is the strategy? So the strategy is by the method of continuity. The method of continuity says that, in fact, what you want to do to prove existence, uniqueness follows from the maximum principle. I mean, it's very easy uniqueness. So in order to prove existence, what you look for is an a priori estimate, in which says, let's assume that I already have a solution U that solves the equation. My goal would be to show that the second derivatives, the C2 alpha norm of U, this means that the second derivatives are Holder continuous in omega, but they are bounded, the C alpha, the Holder norm of the second derivatives is just bounded by something depending on the data, something that I know already. Something like the right-hand side, the C2 norm of the right-hand side, the boundary data and phi, but not on the higher derivatives of U. Yeah, I'm not allowed to use that. I can assume that U is C infinity, that U is very smooth, but in my estimates, I don't need to see that. I don't. So this is known as an a priori estimate. And then how to use this a priori estimate is essentially you go back, and the method of continuity says that give me some solution. Let's call it here. Let me draw it here with a different color. I'm going to use orange. So you start here with some explicit function W that has the same boundary data. And then you compute the square of W, which would be some nice function G depending on W. Yeah? And then your goal is basically to modify GW slowly and transform it into F. And you're trying to do this continuously. You're trying to deform the right-hand side continuously into F and try to solve the equation little by little. When you solve the equation little by little, means that you solve a linear equation, which has estimates as long as the W, or as long as the solution that you linearize around has C2 alpha estimates. Yeah. So as long as you have C2 alpha estimates, means that when you modify the right-hand side, nothing goes bad. You can only solve little by little and go from GW to F. So this is the fact that nothing goes wrong is encoded in the estimate. So as long as the C2 alpha norm of the solution U is not, it just depends on the data, the right-hand side and the data, everything goes through. Yeah. Okay, so at the end of the day, it all depends on this estimate. So how do you prove such an estimate? I'll just sketch what are the main steps. I cannot go into the detail. But the main idea is the following. Let's simplify things. I mean, if you do them in the simple case, you can generalize them. So you say, well, let's assume that F is always 1 and the domain is the unit ball. Yeah. So I know that the determinant of this square of U is 1, and I'm trying to do the estimates in the unit ball. What are the main steps? So the main step is, step 1 is to prove that the second derivatives are bounded. Once you prove that the second derivatives are bounded everywhere, the determinant the Monge-Ampère equation becomes uniformly elliptic. So uniformly elliptic is much better because a uniformly elliptic equation, I mean, there is a theory for uniformly elliptic, a more general theory for uniformly elliptic equations. Yeah. But in order to reduce it to that case, we really need a bound on the second derivatives. After that, the step 2 comes from the theory of uniformly elliptic equations that are concave. So let's say step 2 is basically our operator is concave and uniformly elliptic. And then for this, there is a more general theory in which you can, in first step, you just prove that the second derivative are bounded, but then you can gain a Holder modulus of continuity through Harnack inequality. So this is known as Evans-Krylov theorem plus boundary Harnack to do estimates at the boundary. So this is a bit maybe more technical. You can find these things in, let's say, in the book by Caffarelli. Let me give a reference for this. This is in the book of Caffarelli, Cabré, a book about nonlinear second order elliptic equations. So there is a way, once you prove that the second derivative are bounded, you fall into some sort of better setting, and then you can improve things. Yeah? So I'm not going to say anything about step 2 because that would require a few lectures just to do the step 2. But let's understand how to do step 1. How can you bound the second derivatives, yeah, knowing that your solution solves the determinant of this curve is equal to 1. So to bound the second derivatives, there are like 3 or 4 little steps. So the first step, you say, well, let's first bound the solution U and the derivatives. And one very good thing about the Monge-Ampère equation is that the solution is convex. And once you have convex solutions, they are in the interior, they are automatically Lipschitz. So that's already a lot of information. Just by convexity, your function cannot be very wild. So it's easy to show that the solution is bounded by a constant because you can use barriers. Barriers, you can try to think that if your function here on the right is the graph of it is drawn by U, this is U, your job is simply to say, I'm going to find a more convex function W that is C2 with the same boundary data and with the determinant being bigger than 1. And such a function by maximum principle would always stay below U. So that would already give you a bound on U by below. And the bound by above is sort of obvious because U is convex. So somehow you can prove that U is bounded by C, but not only by C, at the same time, you're also bounding the gradient at the boundary if you find this explicit function. So this explicit function really just depends on your boundary data. Yeah, so you can trap your solution at the boundary, and then in the interior, the Lipschitz norm would extend. The maximal Lipschitz norm for a convex function occurs on the boundary. Okay, so the first part is easy. Using some barriers, you can show that the gradient in U is not so large. How about when you go to second derivative? So the second step is to bound the second derivatives, but not everywhere, but just at the boundary point. So in the second step, you think like this, that my domain is a ball that is denoted here omega. So here, this is the domain, which is a ball. And I pick a point on the boundary. Let's assume it's the origin for simplicity. So I call this point where I'm trying to do my computation 0. And then in the second step, we're trying to bound the tangential second derivatives. So the tangential second derivatives, because I know that on the boundary U is equal to phi, I know that the tangential second derivative if I move on the boundary. So if I take second derivative on the boundary of u, I know them because they coincide with the second derivative of phi. But in terms of tangential derivative at 0, the second derivative of u can be expressed in terms of the second derivatives of phi. And then there is this correction term because the boundary is not straight but is curved. You get an extra term involving the gradient of u that is already bounded by the first step. Or sorry, not the gradient, the normal derivative of u. I guess it's the normal derivative of u minus phi. I guess the term is missing there. And this is u and minus phi. So. And second derivative of the boundary. This kappa ij are the second derivatives of the boundary at the origin. For a ball, this would simply be some delta ij. So the tangential second derivatives are essentially known because of the boundary data. So here I and j are tangential, yeah. And in second step, you also bound some mixed derivative, which means that I take one tangential ui and the second one n is normal. So these are called mixed derivatives. What is the strategy to bound the mixed derivative? U, I, n. Yeah? And for this, you need to differentiate the equation, but you need to differentiate the equation in such a way that you still have information of your data on the boundary. So actually, when you deal with a ball, the way you want to differentiate the equation is to take a vector field tau, given here, tau, which would be tangential to the boundary. So this vector field tau is tangential to the boundary, and it really represents just a rotation in the xi xn plane that is rotated around the center of the ball. If my domain is a ball, it's just the center of the ball, and then the boundary is mapped into the boundary. Yeah, and also the equation somehow is preserved because the equation is preserved under rigid motions. So at the end of the day, the derivative with respect to this vector field, u sub tau here, the derivative of u with respect to u sub tau, which you can try to think as an infinitesimal difference between u and the rotation of it, yeah, solves the linearized equation, L of uw is equal to 0. What is the linearized equation? So the linearized equation, let me remind you, is just what you obtain by differentiating the equation formally with respect to u. So the linearized equation is given by capital Uij, which are the cofactors. So here Uij is the cofactor matrix, cofactor of the d square of u, which is the same as saying that this is the inverse of u divided by the determinant of the square of u, which is, we assume that is 1. So because the determinant is 1, the cofactor matrix is the same as the inverse, yeah? So our linearized operator is always given, the coefficients are given by the inverse matrix of the Hessian Wij, and is, well, at this point, you don't know it's uniformly elliptic. You don't have a bound on this coefficient, but you still satisfy the maximum principle. Yeah. So you have that u tau, L of u tau is equal to 0. At the same point, L of any linear function, if I apply the linearized operator to any linear function, let's write here linear, that would also be 0. Even though my linear operator looks funny, that it depends on u, when I plug a linear function instead of w, because I compute wij, that would vanish. Yeah? So now what I did in the first case using barriers for u, in fact, I can use barriers for u sub tau, and not for the determinant, but for the linearized operator L. Yeah? So you know u sub tau on the boundary because that's the same as phi sub tau is a nice function. And you can always bound it between two linear functions by above and below. So at the end of the day, let me write here, or maybe let's put some, let me try to say here that at the end of the day, what you say that L of u sub tau is equal to 0. but you sub tau on the boundary. So u sub tau is the same as phi sub tau. Yeah, so this is known. And now all I have to do, I have to find linear functions. I have to find L plus at 0 and at minus at 0 that bounds this data, that bounds phi sub tau, which is the same as u sub tau, bound L0 minus, and all equal with all equal at the origin. At the origin. And because L is L of this is a solution for the operator L, and this is a solution for the operator L, you're trapping u tau everywhere, not just on the boundary, but everywhere by these two explicit functions. And from here, it gets that u tau sub n, the normal derivative, is bounded. But this is the same as uin. So uin is bounded. So we managed to bound the mixed derivatives, which is, yeah. After you bound the mixed derivatives, you can use the equation. There is one remaining derivative, which is unn, the second derivative in the direction perpendicular to the boundary. But for that, you use the equation. You use that the determinant of d square of u is equal to f. So the fact that I bound all the entries of the Hessian, and I know except one, and I know sort of I know the determinant, then I can bound the last one. Okay. So in up to step 3, we managed to bound all the second derivative at a point on the boundary. This point is arbitrary, so by step C here, we managed to bound those second derivatives on the boundary. How do we extend them from the boundary inside? And this is where we use the concavity of the operator. This is where it's very important that it is convex or concave. In our case, it's concave. So when you have concave operator, you can try to work with second derivatives. So I claim that when you apply the linearized operator to a pure second derivative of a solution u, this has a sign. Is no longer equal to 0. We're going to see in a second, but this has a sign and makes UE like a sub-solution. It's like a subharmonic function. Yeah. And then this means that its maximum occurs on the boundary of the domain that you are dealing with, but on the boundary you already bounded. Yeah. So for this step, what is crucial here is that our operator F is concave, and then we can take two derivatives. So let's explain a little bit better. So let's take a general operator. It doesn't have to be determinant to the 1 over n. We think here we have an operator capital F. So these are like some general things. How do you deal sometimes with nonlinear equations depending on the Hessian? Yeah. So you think I have f of the Hessian equal to some constant. Then what you do, you want to differentiate in some direction E. E is a unit direction. So you want to differentiate the equation. When you differentiate the equation, you have to differentiate each entry of the square of u. And for this, you call Fij of the square of u. This simply says this is the derivative of f with respect to the ij entry, right? F is a function of matrices. F is a function depending of m squared variables. When I write f sub ij, I mean it's the derivative of f with respect to the ij entry. And then I have to differentiate the ij entry in the e direction, and I get this. And this is exactly what I call the linearized operator. This is L of UE is equal to 0. So the derivative u sub e solves the linearized operator. Now, if I take one more derivative, I have two terms coming out. One by differentiating UEIJ, and this would be, the first term would be L of UEE, because I'm differentiating the UEIJ in the direction E one more time. The other term is sort of a second derivative. I have to differentiate the Fij of this square of u with respect to the E direction. Yeah. But this means that I'm going to get an I have to differentiate with the KL entry. So I'm going to get a term of the type Fij KL of this square of u and two derivatives, UEIJ, UEKL. The way to think about this is simply a second derivative of f in the direction, a pure second derivative of capital F in the direction of this square of UE, right? So it's like this square of UE is a matrix, and this is really just a pure second derivative in the space of matrices. But the fact that F is concave tells us that this second term, that in general you don't know what to do with it, has a sign. Yeah. So it has a sign, and that tells you, well, if this has a sign, then L of UEE has to be positive if this is negative. Yeah. So this is, I try to explain here why pure second derivatives are sub-solution for the linearized operator. And okay, so this essentially proves step one, because from ABC we know the second derivatives are bound on the boundary. Second derivatives are sub-solutions to some second order operator, elliptic operator, so the bound can extend inside by the maximum principle. And then step two, as I said, I'm not going to insist, but these are the main ideas. And what happens here, in fact, I didn't use so much, for example, the precise form of the determinant. This method is quite general and works for more concave operators, not necessarily just Monge-Ampère, but many other concave operators with this theorem of Caffarelli, Nirenberg, and Sprague applies in other situations as well. Okay, so now after let's say we are done with let's say, are there some questions so far? Yeah. So now that we are done with Caffarelli, Nirenberg, Sprague, I'm going back to some example that we discussed in the first lecture, which was an example of a solution that was not C2. Yeah, so this is known as Pogorelov example. So let me remind you that there is a solution to the determinant of this square of u0 equal to 1 that has the form, it's some function x prime. So you think that we are in Rn, we look at one line given an axis, xn axis, and x prime measures the distance to the xn axis but raised to a power less than 2 minus 2 over n. And this is, as I move along the xn axis, this is multiplied, this multiple of the distance to the axis is multiplied by a function h that depends on how far I move in the xn variable. And last time we said that there is such solution that solves the determinant of this square of u equal to 1 and is a viscosity solution. Viscosity solution means that, well, this solves the determinant of this square equal to 1 away from the axis. On the axis, I can no longer take two derivatives because of this term, because of x prime is raised to power less than 2. So on the axis, sort of the x prime, this is the x prime, let's say this is the x prime. Okay, let me just try to draw it slightly different. So this is the x prime direction, and this would be the xn direction. So in the x prime direction, when I sit exactly on the axis, second derivatives are infinite. Yeah, I mean my function is so convex up that all the perpendicular second derivative to the axis when I sit on the axis are infinite. On the other hand, the second derivative along the xn is 0, because my function is always 0 on the xn axis. So somehow on the xn axis, I have some funny thing happening. I have a infinity multiplied with 0. So you are not sure if you really satisfy the equation or not, right? If somebody gives you a harmonic function, says it's harmonic everywhere, but you cannot check at a point, well, it might be the fundamental solution, right? My function might, at that point, might tend to infinity or something. So on the other hand, what we said last time is that this solution, this Pogorelov example, still satisfies comparison with classical solutions. So I cannot touch, even though it's singular on the xn axis, if you give me a smooth solution that on the boundary is strictly above, then also inside it will be strictly above, and the same thing by below, right? So let me convince you that this Pogorelov example is in fact a nice limit of classical solutions. Yeah, and this comes, or in fact, okay, and this comes from what we just did. If you go on the Pogorelov example and you take a little ball, a domain and a little ball around center point on the axis, and you look at the boundary data of U0 on this little ball, this boundary data is going to fail to be C4 like is required in the Caffarelli-Nirenberg-Sprague. But I can always approximate it with C4 data as close as I want. So if you give me any small epsilon, I can always find some sort of data here that follows the boundary data of U0, tinier and tinier and tiny, I mean, with little error, and those solutions are classical. I can solve them inside. Yeah. But these solutions, if I move them a little bit up or down, they would be I mean, the solution U0 has to satisfy comparison with this thing. So somehow you can trap U0, between classical solutions that are closer and closer and closer to each other and that converge to U0. Yeah? So this solution U0 is truly a solution to the Monge-Ampère equation simply because it's approximated as close as you want with analytic solutions that converge to it. Yeah? But they just happen to, in the limit, just happens to have a singularity on the xn axis. So anyway, why do I want to mention this? Because this Pogorelov example says that there is no way you can bound the second, like you can have interior estimates for the Monge-Ampère equation of the following type. If you give me a bounded solution U, let's say you give me a solution U that you already know is between -10 and 10 and solves determinant of this score of U equal to 1. Can I say that in the interior my solution is nice and classical? And you cannot say, because of this Pogorelov example, sort of the second derivatives can blow up in the interior. Yeah. So just pure interior estimates are not available for. So I'm going to write here, yeah, no interior estimates for the Monge-Ampère equation. Here I'm referring to Laplace equation. For the Laplace equation, you don't care about the boundary data. For Laplace equation, you say, well, give me a harmonic function that is between 0 and 1. In 1/2, I can bound all the second derivatives independent of what happens on the boundary. Well, then that's not the case for the Monge-Ampère equation. However, there is an interior estimate, but it has a different form. So I think this is very important. So Pogorelov at the same time gave this example, this singular example of a singular line, but also he provided an interior estimate for second derivatives under the assumption that the function vanishes on the boundary. Yeah. So I would say this is crucial for the whole understanding of the Monge-Ampère equation, this estimate. This is known as Pogorelov interior estimate. So again, we solve determinant of this square is equal to some right-hand side. Let's think is 1. But the key assumption here is that U vanishes on the boundary. So the picture is here on the right. That's sort of on the boundary of the domain, U vanishes. And inside it solves the determinant of this square equal to 1. Then what Pogorelov showed is that I can bound the second derivative inside depending on how far I am from the boundary. When I get closer and closer to the boundary, the second derivatives can deteriorate, because if the boundary of omega has some corner, sort of the second derivative cannot remain bounded as I approach the corner. But as long as I stay a little bit inside the domain, I have second derivatives. Yeah, I have bound on the second derivatives. So going back, this is not, I mean, you cannot apply this this estimate on the xn axis in the Pogorelov example, right? In the Pogorelov example, if you remember, we have this picture where if you try to go on the axis, okay, so okay, maybe let me go. So the function u is always, if we subtract a plane from u, it still solves the same equation if I subtract the linear function from u. So let me go a little bit on the bottom before I go on the top and say, if you give me, I draw here a 1D graph. If you give me a graph u that, let's say, happens to be strictly convex at some point x0. So if it's strictly convex, then what I'm going to do the following. I'm going to look at the tangent line to the graph of u at x0, and then I'm going to lift it a little bit up. Yeah, just a little bit up. And then I'm going to try to pay attention just in this domain where my function is below the lifted tangent plane plus epsilon. Yeah, so here I'm lifting it up by epsilon. Epsilon is very tiny. Because my function is strictly convex, means that my function has to curve up. It cannot exceed the domain. And I get some sort of segment. In 1D, it would be a segment, but in higher dimension, it would be a set around x0, where u minus a linear function would vanish on the boundary of that domain. So in such a set, I can apply the estimates on top, and it would say that at x0, the second derivatives cannot be infinite, that the second derivatives are bounded at x0. So the conclusion is, in fact, that u is nice and smooth at the points. I mean, this Pogorelov interior estimate shows that singularities, that singularities cannot occur at points of strict convexity. They can only occur at points where your function is not strictly convex. And that's exactly what happened in the original example of Pogorelov. Our function was smooth at all the points except on the xn axis. But on the xn axis, it's not strictly convex. When I touch with 0,
there is no sound. The sound is lost.
The interior estimate of Pogorelov. Now, what we are at the point in which we say that the strict convexity plays an important role. Where you are strictly convex, you are automatically smooth if your right hand side is smooth. Okay. So how about this Pogorelov interior estimate? How do you prove a second derivative bound? Yeah, I don't want to, the computation is a little bit involved. I don't want to do it, but just give a rough idea. Yeah. So we are assuming we have to use the fact that u is 0 on the boundary. This is a key assumption. So I know that I solved the equation, but at the same time, u is 0 on the boundary and is convex. Yeah. So the picture is here. So the idea is known as, well, so we do the same as we did before, right? We know that the determinant is 1 for simplicity. This is how we start. We differentiate the equation. We get that the linearized operator of u1 is 0. And then if we differentiate the direction in x1, yeah, the equation. And then as we differentiate one more time, we get that the second derivative has a sign. This is greater than or equal to 0. Yeah. I would like to use this convexity, I would like very much to use the fact that the second derivative achieved the maximum on the boundary. Yeah. However, on the boundary, the second derivative could be infinite. So there is this trick of saying, well, let's try to compute not L of U11, but let's try to cut off U11 by a cutoff function that would vanish on the boundary of omega. Yeah. So it turns out that for the Monge-Ampère equation, this cutoff function you can use is U itself, or absolute value of U. Yeah, so the absolute value of U, your function U looks like this: is 0 on the boundary and is negative inside because it's convex. Yeah. But if you multiply with minus U, with absolute value of U, this would vanish on the boundary. And the good thing is that the linearized operator applied to U, you know it precisely, is just precisely N. It's like some sort of magic computation. The linearized operator is given by the inverse matrix, while U is Uij. So when you compute L of U is just a given constant N. So then what you do is some sort of, you try to cook up some quantity involving U, involving second derivative cutoff, because you want them to be 0 on the boundary. You want to sort of, and then, well, it turns out in Pogorelov computation, you can add some sort of more convex terms, and you try to apply the maximum principle to such a quantity. So it's some sort of product of U with a U11 that you try to bound. You try to bound U11. But the way to do it would be to say that the product of absolute value of U times U11 times some exponential involving the gradient of U cannot be too large. Yeah. So this, in some sense, you're trying to extend this estimate from just a pure second derivative U11 to U11 cut off by something and try to look at the maximum. The computation is a little bit long, but what you can show, you can prove that the maximum of this quantity cannot be too large. Yeah, this M is sort of bounded by the diameter of omega. You look at the maximum point, you apply sort of, let's call this function W. So basically the computation goes like this: L of W, because it's a maximum point, this is less than or equal to 0. And the gradient of W at the maximum point where the computation has to be 0. Yeah, you use this with the information given here by 1, 2, 3. And at the end of the day, you end up that this value of M has to be bounded. What that means, it means in fact that U1, if that value is bounded, it means that the whole product is bounded, but I have information on U, I have information on the gradient of U, so somehow this would create a bound on the second derivatives. I don't want to get too much into details, this is the idea. But what becomes clear after this Pogorelov estimate, it becomes clear that the way to do the estimates for the Monge-Ampère equation is not using balls. Like for the Laplace equation, you want to use balls. You want to say, if I have an information, if I know the behavior of U in B1, then I can conclude something better maybe in half the ball, in B1 half. Yeah, and maybe iterate this thing. For the Monge-Ampère equation, this is not correct. You shouldn't work with balls, because you should work with something that is a fine invariant. And these are what is called sections. This is exactly the picture that you take a point x0, you look at the point on the graph x0 of x0, drawn here like this. You look at the tangent plane at that point, and then you lift it up by h, up. H is very tiny. And you call this SH of x0. This is known as the section of U at x0 of height h. Yeah. And the way to think about this is like x0 is the center, and SH of x0 is like some sort of ball of radius h around x0. But of course, this ball depends on you itself. So somehow we are if you give me a different u, this is changing with you, this SH of x0. So it always depends on this SH of x0 depends on you itself. That's how it's defined. However, the Pogorelov estimate says the following, that if SH of x0 is completely included in your domain omega for very small values of h, in other words, if I'm strictly convex at x0, SH of x0 would be included in omega, then inside I know that u is very nice. I know that u is smooth inside. Yeah. Okay. Now, yeah, so now we sort of have to take advantage of the affine invariance of the equation, because I can take this picture that I see here on the right, and if I apply some linear deformation, the linear deformation applies as well to the graph, and I change the shape maybe of this SH of x0. So here is an important lemma from convex analysis known as Johnslemma, which says that if you give me K a bounded convex set, so you give me K here, a convex bounded set in Rn, you can always do an affine deformation for it and make it look round. Yeah? Or in other words, let's say the lemma says that there exists an ellipsoid E such that x0 plus E is included in K, but this is included in x0 plus a dilation of it. So the picture here is the following. K is a blue convex set. Then you can always find an ellipsoid E here denoted, drawn in red, the inner ellipsoid that stays inside E. But when I dilate that ellipsoid n times with respect to its center, the set K must be contained in it. And then after you do an affine deformation A, you can transform this ellipsoid in a ball, and the picture looks like, after an affine deformation, your convex set looks round. By looking round means that I have a ball inside of it, but it is contained in n times the dilation of that ball. So this is known as Johnslemma. I'm going to try to prove it on the next slide. But why is this important, right? Because this is important, saying that essentially all convex sets modulo affine deformation, they are more or less the same as balls. But to end up in the setting of a ball, you have to do an affine deformation, yeah? Which in our case sort of is very good because we are dealing with an affine invariant equation. Yeah. So whenever, I mean, this ellipsoid E is called John's ellipsoid, and we say that K has the shape of E. I write like this, that K is equivalent to E. But this really means that I have an ellipsoid E inside K, and when I dilate E by n times, or by a bigger constant, it contains. Yeah. So then how do I, when I go back to the Monge-Ampère equation, how do I do things? I take this deformation A here, and I scale space. Well, A, I think was supposed to be the other way around, so it goes this way. Okay. I subtract u minus the linear function plus h. I scale it to preserve the equation so that I don't change the right-hand side. And then in the rescaled picture, I have a u tilde that solves essentially the same equation, but the difference is that now its section, in the set where u is less than 0, is round, looks more or less like the unit ball. Okay. And then we can try to do something with this normalized solution. So I would call this u tilde a normalized solution. So it's essentially just an affine deformation of u minus the linear function. Yeah? It's like I go in the previous picture here, I take what I see here with blue, like this, and I do want to find the formation to the, which means also that the green, the projection down, gets defined, deformed by the same thing and make it round. Okay. Now let me just give a quick proof of Johnslemma. So this is independent of anything. It's like a nice little fact of convex analysis. Why I can, how do I find this ellipsoid? Yeah. So the ellipsoid is obtained by dilating, no, by taking the ellipsoid of maximal volume inside your set. So you take the, you just inflate an ellipsoid more and more and more and more and more till you cannot do it anymore. Yeah? So you take E, the ellipsoid of maximal volume including K, and then I want to say that when this is the ellipsoid that I'm looking for. Yeah. Okay, so my job is to show that when I dilate E n times, the set K would be included in that. Yeah. So let's say, so here, so goal, what I want to show then that n, when I dilate E by n times, this is contains K. Yeah, and this sort of I know by definition, but I want to prove the other inclusion. Without loss of generality, I can assume that E is the unit ball because I can do an affine deformation to E and K. I'm working with the affine deformation of K, right, instead of K itself. So without loss of generality, I can assume that the maximal ellipsoid inside K is in fact the unit ball. Yeah. And my goal then is to show that my set is included in n times the unit ball. What is the idea? Let's say that the point, the picture is here on the right. Let's say that the point on the set K is far away from the origin, very far. Maybe think about tending to infinity. By convexity, the red ball, that is the E in our set, E in our picture is the red ball. This is included in the set. So the red ball is included in the set. Yeah. I can try to, and this blue point here tends to infinity. By convexity, I would get here that the whole, strip, and this ball would be included in the set K, because that's what this point that tends to infinity, and the red ball, the convex hull of it, would generate a whole strip. Now in the whole strip, for sure, I can find a big ellipsoid of large volume, bigger than 1, and I contradicted that the unit ball is the ellipsoid of maximal volume inside. Now, let's try to quantify this argument more precisely, right? So if you try to quantify precisely, let's see. So let me try to. Okay, so the way to do it is to say, let's say I have a point here at some distance away from the origin. I look at the cone generated by this point and the red ball, and I want to stick in it an ellipsoid of still volume 1, but it's like an egg. I make the axis along the xn variable a bit longer, and I push it a little bit inside in the x. So I do this to the red ball. I push it like this and pull it in the xn variable. I'm assuming this is the xn axis, the vertical distance. So when you look at so the question is, where does the new ellipsoid pop out of the unit ball? Yeah, this is the question that I actually have to understand. If the orange egg pops out inside the cone, you are happy because that would tell you that you are still inside the set. If the orange egg goes outside of the blue cone and the red ball, then that's bad because you don't know you're still included in the set K. So one does a small computation here. So the equation of the red ball is the unit ball, is the sum of xi squared equal to 1. The ellipsoid that you're trying to stick inside your set would be centered at distance epsilon from the origin in the xn axis. So sort of is centered at, that's why I'm using here xn minus epsilon. And the axis, the length of the axis in the xn variable is 1 plus epsilon. So that is still goes to the bottom point here. Then in the other variables, I shrink a bit, but I have to shrink by this amount because I want the volume to be the same, to have volume the same as the unit ball. So the product of the axis of the ellipsoid should still be 1. And then to see when the orange ellipsoid pops out of the red ball, you essentially have to look at their difference to understand what is bigger, what is smaller, but the difference sort of is the same as taking a derivative with respect to epsilon. You see, when epsilon is 0, the orange thing is the same as the red thing. But when epsilon increases, you want to say, what is the derivative with respect to epsilon? So here is the computation for the derivative here. And essentially, this where the derivative is 0, it will tell you that is the region where the orange and the red ball intersect infinitesimally when epsilon is tiny. Yeah. And when you solve this is a quadratic equation in xn, and you obtain that xn is -1, which you knew already that the two things coincide on the south pole, because that's how you did them. But I actually also get that xn is 1 over n, which means, in fact, that the orange egg pops out of the unit ball at distance 1 over n away from the origin. Yeah. So it doesn't matter how small is epsilon. Epsilon is very tiny, but this region does not depend on epsilon. It's fixed. It's a 1 over n. And that would tell you, well, if this is 1 over n, if you want this region to be contained, in your cone, then you compute that this distance has to be n. So this is sort of the proof of Johnslemma. It says that you cannot have points outside of Bn. Okay, well, time is essentially up. I was planning to say a few more things, but we're going to continue next time. We're going to understand how this Johnslemma plays a role in the rescaling, and next time we're going to talk about Caffarelli's interior regularity for the Monge-Ampère equation. But we are essentially there. Johnslemma plus this interior estimates of Pogorelov sort of show the correct way to scale the equation and to use this information. So I'll continue next time.
Okay. Thank you very much. Are there any questions that people would like to put in the chat?